Alright guys, next video, looking at Dalton's law of partial pressure. This was something else we really didn't talk much about last year. So first off, what we have to understand about partial pressure is go back and remember what pressure stands for anyways. Remember, pressure is the amount of collisions on the walls that the gas are being able to produce. So the more gas in the container, the more collisions that are going to be occurring, therefore the higher the pressure, and vice versa as well. So what happens when we have a mixture of gases? Well, the mixture of gas and the amount of collisions relates back to the amount of moles. So think like bouncy balls. If I take a sealed box or a sealed room, whatever you want to think about, and I throw 20 blue bouncy balls and 20 green bouncy balls, okay? Well, equal amount of each balls being thrown, or each color balls being thrown, means that they're going to be colliding roughly about equally, which means their pressures are going to be about the same. Well, then how do we get the total pressure? Total pressure would be the total amount of collisions, being that the amount of collisions of the blue and the amount of collisions of the green. So that's where we get this first kind of equation here. Total pressure in a system would equal the pressure of each individual gas present in the container. So each set of collisions. So again, let's say I have my box, okay, and I throw 5 blue balls in here, okay, and then I throw 2 red ones, and I throw 8 green ones. Okay, what we have to think about here is, first off, they're all in the same system. Therefore, they all are going to have the same kinetic energy, or at least we're assuming they have the same kinetic energy because we're assuming that they're at the same temperature. It will just make our math a lot easier. So if they all have the same amount of kinetic energy, they're all moving around about the same amount. Yes, we do have a velocity difference, and therefore we're going to have a force difference, but the amount of collision should be about the same for all of them. Okay, so who is, or at least for each individual ball will be about the same. Which color is going to be colliding more often with the walls? Well, the green, because there is more of them. Which color is going to be colliding the least often with the wall? The red. Okay, and that is all taken in consideration. Now, how do you get the total pressure? Total amount of collisions. So we would have the pressure of the green plus the pressure of the blue plus the pressure of the red, and that all added together would give us the total pressure in this container. So really, another way we can look at it is understanding that it's really just a ratio of who's present versus how many are present. So we can also get it from kind of a mole fraction type thing. A mole fraction is really just looking at the number of moles for each individual species over the total moles in the container. So again, back to this idea. If I wanted to know my mole fractions for my red, well, there are 2 moles, if we're assuming each one of these dots represents a mole, for a total of, what do we have, 8 plus 5, so we have 15 moles total. Because we have 8 greens, 2 blues, 7 reds, yeah. So we would have a 2/15 ratio. If we were looking at the blue, it would kind of be the same idea. Our mole fraction would be 5/15. And of course our green would be 8/15, okay? And these mole fractions actually correlate to their pressure fractions as well. What I mean by that, again, is the ratio here will be about the amount of times they collide. So if there's only 2 moles out of 15, you're going to have significantly less collisions here, therefore less pressure being contributed by the red, versus the green. If I have 8 of them out of 15, there's going to be a lot more collisions. So we would assume the green is going to have a higher partial pressure, which I'll abbreviate as PP, versus the red is going to have our lowest partial pressure. Okay, if that makes a little bit of sense in terms of the amount of collisions. So we can kind of use these to do some of our calculations. So let's look at this. Okay, a flask contains 0.25 moles of SO2, 0.5 moles of CH4, and 0.5 moles of O2. The total pressure in the flask is 180 millimeters mercury. What is the partial pressure of SO2 in the flask. And you actually do have this equation on your formula sheet, by the way, so you can kind of pull it up and look at it. But let's just kind of talk logically for a minute here. Okay, 0.5 and 0.5, same amount of moles, it'd be the same amount of molecules, because remember, a mole is just correlating to the number of molecules. Therefore, CH4 and O2 are going to be colliding about equally with the walls, therefore have the same amount of pressure that they are contributing. So these two would have equal pressures, partial pressures. Okay, notice the 0.25 is going to be about half of the CH4 and the O2 because it's half the mole value. So it'd be like having 2 of these and 4 of each of these. Okay, just so you can kind of get an idea of how that ratio works. Now, the actual equation. Why don't you pull out your formula sheet if you haven't, and let's look at this. Okay, and it's on the gases, liquids, and solution side if you haven't already found it. And notice it is the second equation down where we have our PA, which I always say is our partial pressure, A being individual substances. I just write it as P. You can write it either way. Equals our total pressure times our XA or XI or whatever, or X partial. It's our mole fraction is what this is. So just kind of think about what this is actually meaning. Okay, this is a ratio. That ratio correlates to our partial pressure. So if I take that ratio, or maybe percentage might be another way to kind of look at it, multiply it by my total pressure, I can get my partial pressure. So if I'm looking for the partial pressure of SO2, and I'll replace the P now with the actual substance I'm looking for, times the total pressure, which we're told is 800, times its ratio, which is going to be 0.25 moles of SO2, divided by 1.25 moles total in the system. Okay, and again, that comes from 0.5 plus 0.5 plus 0.25. So if we kind of think about it in the regards of 25 out of 125 is 1/5, so it would be 20% of the 800. So we get a pressure, or partial pressure of SO2 to be about 160. Now we could take that one step further if we wanted to and recognize and kind of calculate the other one. So we know SO2 will be twice that big, so 160 times 2, or sorry, not SO2, CH4, sorry. Pressure of CH4 is twice as big, so it would be around 320. Okay, and the pressure of O2 is equal to CH4, which would also be 320. So if we added those all up, guess what we get? We get 800, and we can kind of see how that split works there. Okay, let's look at another one. Okay, and actually what I'm going to let you do, I'm going to let you kind of pause the video for a second, look through this. I want you to see if you can answer all of these, because at this point in time we should be able to answer all of these. Okay, and we'll come back and talk about this momentarily.